All right, let's pick up where we left off on chapter 2, and we want to kind of go into more of the how these molecules or these atoms interact, based now with the knowledge that we have of the octet rule. I want you to think about that in order to make the atoms more stable, they need to have that interaction with uh, other types of atoms, or the same type of atoms in that regard, to try to share some of those electrons, or to provide more stability by filling those empty seats. Now, you think of the octet rule is that for the ones that we're worried about, is having 8 electrons in the outer shell, and each element of course has a different set of numbers of those available seats, or in other words, it's not fully octet ruled. So it's 6 maybe, and it has 2 empty seats to make the 8. So it would want to somehow pair or share, or whatever they want to do, to fill those seats. At least it's more stable than it was without having that interaction. So that's what it's sort of the driving force. Now, why this happens with charge and the like, we can measure it, we can look at all sorts of things, but what drives these is the quest for more stability. But it's interesting. If you go deeper, it's a little bit harder to understand. So molecules are groups of atoms held together by bonds. So bonds are interactions between these atoms. Bond energy is dependent upon the atoms involved. In other words, how many of the shared empty seats, those sorts of things. Chemical reactions involved in forming and breaking of bonds. So you have the reactants, and then when they come together, they're products. And that's really all there is. Now, understanding the interactions of these sorts of things, that's the fun part, and we're going to be talking really about this for the rest of the semester. Now, I do 3D printing at Wake Tech, so from time to time I may make reference to a model. Being online, I'll give you the 3D version of it that's electronic, so you can look at it and rotate it and do that sort of thing. But if you are interested, and I am spending some time on main campus. I don't know what the rules are yet as far as students going on campus, but I have these models in my office there. So anyhow, you can look at those whenever you get a chance if you're interested. So the models that we typically use, now this was set up by this modeling was really pioneered by a lab at a group that worked at a lab at Duke University, and the scientists there had actually come up with these proposed hand-drawn model representations, and kind of set the standard. So the Lewis model is showing the sharing of an electron with a line, or you can draw it with a ball and stick type model. And I 3D print the space filling model, so you can see sort of the orbit of the hydrogen, the orbit of the carbon, as far as the electrons in that random distribution. So we just represent them as circles, and the hydrogen is somewhat embedded in the carbon because it's sharing the electrons. And you can see carbon, as far as the octet rule, is only 4 filled. That means 4 are unfilled. So we fill them with 1, 2, 3, 4 hydrogens to satisfy the octet rule. And it's really that's straightforward. And so the types of bonds we're going to go over. And remember, the bonds are dependent upon the atoms involved, and the forming and breaking of the bonds we refer to as the chemical reaction. So let's go into covalent bonds. And these are the types of bonds that can be formed between atoms of the same or different elements. The compounds is a combination of 2 or more different elements. Bonding capacity is called the atom's valence, outer orbit vacancies. Now, I brought this term up in the last presentation, and the valence, if you remember, is sort of like the bumper in the car. In fact, I think they still refer to some of the bumpers, the front or rear, as the valence of the car, or the outer valence. But it just means it's the number of available seats because of the octet rule. So you're well ready. You already know that term. So the outer orbit vacancies are the seats that are not filled for that octet rule. So carbon has 4 available seats. So that would be its valence number. Pretty straightforward. So just to review, the octet rule is a chemical rule of thumb that states atoms of a main group element tend to combine in such a way that each atom has 8 electrons in its valence shell of the ones that we're worried primarily about. So as we go beyond the elements that we're talking about, that rule is a little bit different. But well, let me show you what I mean by that. Here's the octet rule as it is available for hydrogen, helium, lithium, barium, boron, calcium, nitrogen, oxygen, fluorine, and neon, sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, and argon. And we can even go on further. We have potassium, calcium, gallium, germanium, arsenic, selenium, bromide, and krypton. So those, you can see the octet rule and the valence number as we go across, and it's the same: 1, 2, 3, 4, 5, 6, 7, 8 in the outer. But that, don't forget, the inner orbit has 2 always. All of these have that satisfied inner orbit. It can't form the outer orbit until the inner one's filled. So that's assumed. So you really have 2 more than that. So that's 5, 6, 7, 8, 9, 10, 11, 12 in terms of the total number of electrons. And 8, 9, 10. Oh, it's 10. I got that wrong. It's listed right there. All that means is that we have 1 and then the 2 of the inner valence. That's what I should have said. And it goes across. So now you're starting to see the relationship of the periodic table as we go up and down, because we add an orbit, and then as we go across from left to right, we're filling each of the available seats up to 8 for the octet rule. And so that's the relationship of the periodic table. And we can show satisfying the octet rule. Now I use dots just to represent the sharing of an electron. And so the carbon belongs, these are the red, and the carbon has 4, and it needs to fill, if it can, at least share through a process of temporarily providing. So the hydrogen thinks it has 2, it fills its octet, and carbon thinks it has all 8. But what it's doing is forming a covalent bond with each of these, and this is what makes the chemistry, this is what makes life work, is these interactions and building blocks like Legos. And so the carbon always will have 4 available, and CH3 is a very common a compound, so a molecule in this case. So if we look at the formation of the CH4, we have carbon and the hydrogen on the periodic table, and you can see that based on the octet rule, this needs 1 more and this needs 4 more. And so it's 1, 2, 3, 4 as we go across, and that's the octet part. Now it has 6 electrons, but 4 that occupy the outer shell, and so we refer to that as the octet, or the valence number is 4, because it needs 4 more to fill the seats. So I hope that makes sense to you. And sharing electrons becomes more stable. So that's the idea, is it's a win-win. A win for carbon, it's a win for hydrogen, and all the way around. So CH4 is a really good arrangement. So covalent bonds, like cohabitating, if you think of it that way, is sharing. So we have hydrogen, hydrogen, and we have H2. So we can have hydrogen bond to itself and get the H2 molecule. Now that's totally allowable. I mean, it could be of the same or different, and its characteristics will be largely different that way when it's bound up as H2, because now it's sharing, and it's at least more stable than each of these alone, but together it's a little bit more stable. So the two atoms share the electrons. The electron cloud surrounds both atoms, so it's at any one time one of the hydrogens can account for two, but not all the time, of course. It goes back and forth and shares back and forth that way. So it's a single covalent bond and a double covalent bond. So a single is when it's only filling one for each. Okay, that's a single covalent. And a double covalent is a good example, is O2 molecule, and we have O2 now sharing two electrons, and that would be a double. And so the O2 or molecular oxygen O2 molecule is represented here by sharing the two. And then methane, that I've already talked about, is that we're sharing 1, 2, 3, 4 of each of those hydrogen bonds, but that is a single covalent bond on each case. And this is a double covalent bond, and so that's pretty straightforward. So in a non-polar covalent bond, the atoms share the electrons equally. In a polar, now what they refer to as non-polar and polar is having a charge. Think of it as poles of a magnet. You have a sort of a positive and a negative, and they either repel or attract based on the charge. A positive negative will attract, and negative negative will repel, as well as a positive positive end. But that's polar. Polar, one atom is more electronegative, and the atoms do not share the electrons equally. So I threw in a term right away that we haven't talked about, is electronegativity. And this becomes a point of consternation for some, as when you take chemistry and the like, but not to fret at all. I'm going to explain electronegativity. And first of all, I'll tell you, we don't understand it. The Linus Pauling actually got a Nobel Prize. What he did was, he actually holds 2 Nobel prizes, but a brilliant man. He actually came to NC State once. I got to meet him. Is interesting. He's gone now, but it was a privilege to be able to meet with him. The graduate students got to have lunch with him. It was really cool. But anyhow, polar covalent bond is as a result of uneven cloud distributions. And I'm going to go over this, but I just want you to think of it as it's measured, and the electronegativity of each of the atoms have been measured. And what we're measuring we don't really understand, but because of the difference in electronegativity, you get an unequal sharing upon this similar type of atoms. So the more electronegative one atom is to relative to another when they bond, there'll be a charge difference at one end of the molecule versus the other, and I'll show you what I mean by that with this simple little drawing. Electronegativity is a tendency of an atom or functional group to attract electrons. So the hydrogens are bonding at 104 degrees, roughly, off of the oxygen here, as you can see. And it sort of groups that electron cloud, and it's just the sort of the laws. But oxygen is electronegatively larger than the hydrogens, and so it leaves this little bald spot. Now, you haven't seen me in person, but I have a little bald spot as well. It's not due to electronegativity, it's just, well, age. But it's balding up here, and what the result is that with the sharing or redistribution of those electron clouds, we get a sort of more of a positive charge at one end of the molecule and a negative at the other, and that's the polar charge. The polar is like a linear magnet that has a positive and negative, so the positive pole would be here and a negative, and that changes how it interacts with others. Water molecule is without a doubt the most important molecule that we could talk about. And this is the first thing they look for if they want to try to understand a planet to see if it can support life, is they look for water, because it seems to be the universal solvent. It seems to be required for life, and it's a universal solvent because it can interact with any molecules that are positively charged or negatively charged, and it'll align and flip around as it's needed. So that gives water some special properties, and we're going to talk about those. But that's important. So electronegativity is an atom's attraction for electrons in a covalent bond. The more electronegative, now again, we don't understand why, we just measure it. So that's all Linus Pauling did, is he measured these, and he gave a value to each of the atoms in the periodic table. The more strongly it pulls shared electrons towards itself. So that's the net result is the electronegativity strength. The more electronegative, the stronger it can pull shared electrons towards itself. And here's sort of a diagram of that water molecule. And you can see that the blue represents more of the positive charge, and we go to the negative. But really what that previous discussion was, that we get this distribution as a result of the electronegativity of the carbon pulling more tightly at its bond angle of the two hydrogens, leaving a region that is negatively charged. And that's all there is. Now, in chemistry, when you take that course, if you ever decide to do that, the concept is actually displayed in a little bit more terms of math and that sort of thing, but don't lose sight of what's actually happening. And here is what Linus Pauling found. He assigned electronegativity, so the darker the red, the more electronegative. And they call this the Pauling scale because of Linus Pauling. And you can see oxygen, nitrogen, carbon. So carbon is more electronegative, let's say, than sodium. Let's see. So we have 204. Hydrogen is more electronegative than, let's see, more electronegative than boron. So anyhow, you can see the relationships, and based on it, these are measured. We don't understand why. And that's all I want you to know is that the more electronegative that these covalent bonds interact with other atoms on the scale determines if it's going to be polar or nonpolar. And that's all that's about. But it took a little bit to explain it. I hope that makes sense to you. So now, a second type of bond, we just talked about covalent or cohabitation or sharing type. Here's ionic. These are ions. So ionic bonds, and atoms, electrons determine whether or how the atom will bond with each other. Electron shells and stability, remember just the vacancy, the valence and vacancy, same sort of term if you think of it that way. So atom stability, unstable because it needs to fill it, but helium has both, and so we know that it's very stable. It's inert, as we talked about. So only when atoms have electron vacancies in their outermost shells are likely to interact with other atoms. So, of course, I mean, that is the furthermost portion. Now, in ionic bonds, what's really interesting, the first thing I want you to observe, is the chloride atom has all the valences except one. So in theory, it would be a lot easier just to add one more than to interact and just do a covalent bond, which it could do. But in ionic bonds, it changes the overall characteristics of the element that we're talking about, and it takes on a new name. The element is still the element, but we have to call it an ion, and that's what an ion is. So sodium has just one flying around in its outer valence, so it needs outer orbit, so it would need for the octet rule to fill 7, and that's pretty high demand. So it's actually easier for the sodium to give up one electron, and sodium would become a ion, and because the electrons are negatively charged, it would be a sort of a positive associated ion. So a sodium ion would be positively charged, and when chlorine takes that donated electron, now it becomes a chloride ion. It would have now an extra negative electron, so it takes over a negative like charge. Based on that, sodium and chloride will bond to each other due to the opposite charges. So because the chloride ion is now negative and the sodium is positive, they'll attract, and of course that forms table salt. And water can disassociate those bonds, the ions, pretty quickly, but within, let's say, drying it, the sodium chloride ions would crystallize and you form these crystals. And really interesting. So the two oppositely charged ions attract each other. Ionic compounds are neutral because they've satisfied that that bonding or that charge. So it's binding with the negative with the positive, so it's no longer charged at that point because they're held together. And so that's pretty much what's going on with these ionic bonds. So carbon is available, of course, as we've already talked about, with 4 valence electrons. So the octet rule, to satisfy the octet rule, we need 4 more electrons. A huge variety of complex molecules are possible. Carbon bonds with oxygen, hydrogen, nitrogen, and other carbons. And so we know in covalent bonds that's the case. But unfortunately, ions, or fortunately, however you want to look at it, we have to have close to the full complement of its outer shell for, like in the chloride, and the sodium is all but 1. So as I say before, I'm just reiterating, it's easier for it to lose 1 to become an ion, and chloride to gain 1, so it satisfies its full octet, and we call it an ion. And there you go. So they're charged. So I want you to separate the two covalent type bonds, like the carbon, and filling it in as sharing. But this is the actual donation of the electron, and when it does that, it takes on a new characteristic called an ion. So typically we've seen atoms have the same number of electrons and protons. Sometimes an atom may have 1 or more extra electrons that lack 1 or more electrons relative to the number of protons. The atom with the extra electrons becomes negatively charged. We know that because electrons are negatively charged, and the atom lacking 1 becomes more positively charged. I just thought I'd state the obvious, but it's always good to do that. Such charged atoms called an ion due to the electrical charge. Ions behave very differently from the atoms that give rise to them. So once they become an ion, they take on a totally different type of electrical characteristic. Now with water being bipolar, we've already talked about the water molecule, H2O, and we have the hydrogens, and the oxygen being more electronegative leaves the positive ends where the 2 hydrogens are, leaving that bald spot of the negative. It'll associate with the sodium, and we have that ability. So the water molecule can flip, and now the positive part of that water molecule can associate with the chlorine ion. So you can see that the ions are separated because the water will flip around. That's the bipolar nature of water. And so we can have potassium chloride, and water will do the same thing. It associates with its opposite charge, and the molecule just flips around, so it's a negative or positive. And that's what we mean by bipolar type of nature of water. And then these are ions that have taken on new characteristics based on the fact that they've added or lost an electron. And that particular case is called an ion. Now there's one more type of bonding that we are going to talk about. We've already talked about covalent and ionic bonds. Now we're going to talk about hydrogen bonds. So hydrogen bonds, on the other hand, are important in bonding multi-atom molecules together. Hydrogen bond is formed between hydrogen in one molecule and another molecule, often an oxygen or nitrogen atom. And hydrogen bonding is without a doubt the most interesting type of bond as far as I'm concerned, because you're going to hear this term or this phrase I say, individually weak but collectively very strong. This theme is throughout all of life. It's fascinating how this very simple hydrogen bond can actually make a huge difference in life. It's incredible, and it's so simple, and a lot of times you just talk about it and you shuffle it and you forget about or don't really discover how important this is. So let's look at it. There's that magnet I talked about with a positive and negative ends. Magnets are like that, so it's polar. And remember, water molecule, because of the higher electronegativity of the oxygen than hydrogen, it tends to pull it close to itself at the bond angle of 104 degrees roughly. And so as a result of that, you get more of a positive charge at one end of the molecule and a negative charge at the other because of the bald spot. So water is like that. And what I've already demonstrated it covering the ions. It flips whatever charge because it has both. So hydrogen bonds bond molecules together. Bonds form between a slight positive hydrogen atom molecule and a slightly negative atom in the other molecule. Resulting bond is weaker than covalent or ionic. So this is the weakest bond is the hydrogen bonding. And you can see the positive and negative aspect of water. Remember, we said water was bipolar, and because it has opposite charges on the poles, it means that it can interact. So there's this cohesiveness in the water. Now, let me ask you before I go into this too much more. How many have ever jumped off a diving board and did a belly flop? Now, that water, of course, has these very weak, I just told you they're weaker than covalent ionic bonds. The hydrogen bonds are really, really weak. But when you do the belly flop, you're just jumping in just a big, pool of water. But I did this, of course, in front of all my friends at State on a high diving board. And I did a belly flop so loud you could hear it across campus. It hurt. It was like landing on cement. And what I can tell you is when collectively these hydrogen bonds seem pretty hard to me at that point in time, they're very strong collectively, individually very weak. And I'm going to give you some sort of view as to how weak I'm talking about. But that interaction between the water, the positive and negative aspect, the bald spot and the hydrogen ends, they form this very weak bond. We call that a hydrogen bond. So the types of bonds are covalent, ionic, and hydrogen. This is the weak. So I just want to kind of, just do a sanity check. So we've talked about the covalent and ionic, and we're talking about the hydrogen bonding now. Let me apply some of the ideas behind this bond as being weak. These are strong. And let's chat about that. So everyone's seen the Geico commercials. Here's a gecko, and it can defy gravity by climbing up a wall. Well, actually, it's not defying gravity really. What it's doing, it has little hairs on its toes, and each hair will have a weak attraction for whatever material on the wall or whatever is climbing up. A very weak, we call that attraction, that hydrogen bonding attraction from the positive negative, is called a van der Waals force, and it's a very weak force. But collectively, when you add lots of these together, it's collectively much stronger, and so the gecko climbs right up the wall. And it's because of the formation of all these little hairs, and has that van der Waals force due to the hydrogen bonding. It affords its ability to literally have enough traction and attraction. It will have ability to walk right up a wall. or in a ceiling or whatever. Now, I was in a startup company, pretty long time ago, and in other words, it was funded by venture money, and so we were trying to develop some stuff. The fellow next to us was a really interesting fellow. He was uh, in the Navy. I guess he was did special ops and all these fascinating, amazing things. And one of the things he came up with was a device that could do a listening in device. It was used for surveillance and various things during wartime, and it was like a little truck, and he could actually drive that truck remotely right up a wall using this same concept of these little hairs. And he didn't use hairs, of course. He had materials that had similar characteristics and individually weak but collectively very strong. He could drive the listening device right up a wall and hide it or put it in places. It was really small. It was quite amazing. So he shared that design with us. He was a Navy SEAL, and a really interesting fella. Um, just amazing to be able to talk with him about those sorts of things. But it's millions of small projections adding just a little bit of attractive force. So collectively, it's very strong. Individually, very weak. And you can demonstrate this, and I usually do in class. I get two brutes out of the classroom there, and I put one on either side of the phone book, and I interleave. Oh, I'm sorry. A phone book used to be a listing of phone numbers of people, so you can go by name and find people. I know, I'm just joking. We don't use phone books anymore, really. But anyhow, you interleave the pages together, and the attractive force of each page with the other page gives just a very weak. If you interweave just two or three, let's say 3 pages, you can easily pull it apart. But collectively, when you do all the pages together, it becomes a solid object. It is amazing. And you may have seen this on the TV shows. I forget the name of it, but they would show how strong this interaction was. So I'd have the two students pulling the phone book, try to pull it apart, and they couldn't do it. And it's that strong. So it just shows you individually weak and collectively very strong concept. And you can see that he actually bolted these in and had two bulldozers in this case, and trying to separate the pages. And eventually it did come apart, but it took huge amount of force between these two tractors. And so anyhow, very interesting. I think that illustrates individually weak but collectively very strong. So hydrogen bonds are formed between slightly positive charged hydrogen atoms of one water molecule and slightly negative charged atoms of another. And it doesn't have to be water. We can have water and ammonia. If you always wondered why we use that for cleaning glass and that sort of thing, is because there is a weak hydrogen attraction between ammonia and water, so it easily goes into solution. And of course, having more of a positive charge at one end tends to make it can bind to dirt and things and use it for glass cleaning, having all that that positive charge. Anyhow, we have the weak attraction, hydrogen bond. It's the same strength really as just water itself, but given the fact that we have this positive negative, for the same reason, nitrogens, you can go back and look at the chart, has a higher electronegativity value than the hydrogens. We don't know why. We measure it though, and leaving that bald spot. So we have the positive down at the bottom because of the hydrogen area, and then because their bond angles are what they are, it pulls away and reveals the sort of the negative charge, and that's why it's bipolar, and it can interact with water with the same sort of thing. So van der Waal interactions is really what they refer to, and of course it was named after Johannes Diederik van der Waal. It was named after he discovered the value. He can actually measure it, And the van der Waals interactions is about as strong as taking a helium-filled balloon and putting it near your hair. Now, if I had hair, I could try to demonstrate it, but I think everyone's had a chance to touch a balloon or to see this sort of effect. But the strength of that is about the strength of a van der Waals force, and that's roughly a hydrogen bond, just so that uh, you can see that. And other applications or how these things apply is we have the bug that has on its little tippy toes here some sort of repellent, water repellent substance, a wax probably of some kind. And because of the hydrogen bonding of the force between the molecules, its weight distribution with all the legs and everything affords its ability to walk on water, essentially, and it's taking advantage of this collective nature of the hydrogen bonding. And again, this is the same water surface that I talked about doing a belly flop on. And so that force is quite amazing at that one moment in time when you hit it. But with the insect, you can see that it doesn't overcome the hydrogen bonding, so it wouldn't come apart. And it's just amazing. And so these little creatures can literally walk on water. So let's review. So we have the covalent bond is the strongest, ionic bond is sort of the next strongest, and then the weakest is the hydrogen bonding in that relationship there. And so this is important. Please see this relationship. It's really straightforward. We talked about all of these. And so when we get to the charges, these two are more similar, and they are the ionic type is stronger than the hydrogen bond, but this is more of a chemical positive negative type of attraction, where covalent bonds you're literally sharing the electron, and that's the strongest. So if that helps you remember that, because these two are more similar in terms of charge, and this one is due to physically at the atomic scale sharing electrons. Hope that makes sense. So atoms can be bound together in three different ways: covalent, ionic, and hydrogen bonds. Covalent are formed when atoms share, cohabitate. Ionic bonds are atoms that transfer its electrons to another, and the two oppositely charged ions are attracted, so they take on, due to the addition, it would be a negative charge, or when it loses that electron, it has more of a negative, positive charge for that ion, and then they'll attract. Hydrogen bonds, which are weaker than covalent and ionic, are formed from the attraction between hydrogen atom, which is bipolar, with another bipolar atom with slightly negative charge. And so that's the summary there. But water molecules easily form the hydrogen bonds, giving water this great cohesiveness due to the interactions of van der Waals forces and the like, which we've talked about. Now, the trees, if you've ever wondered how it gets water from the ground up to the very top of some of these really large trees, there's sort of a siphoning effect occurring because of the cohesiveness of the water. At least this is the current theory. There's some that would disagree, but there's this a little bit of a siphoning effect. In other words, the water is evaporating as it gets up into the upper part of the tree, and because of the cohesive nature of water, it literally pulls it up. Now, if you've ever used a siphon to siphon something, you know that it defies gravity, because of course it's moving against the forces of gravity once you get it going. And this is what we kind of see with trees. And it's this cohesiveness of the interactions between the water, and it helps pull it up, and the evaporation at the very top of leaves and various things, which occurs throughout the entire tree, but collectively it provides that siphoning effect. Now, you've always heard of xylem and phloem. Water molecules will move, and it literally is like a tube. If you look at the distance in the inner portion here, it's just like a rubber tube. It siphons, and the phloem it does a little bit sort of like our veins in our legs. We have little valves, and water can move up, and it kind of holds it in place as it moves up. And we have these the little your sieves, plates that in between. And that's, I just thought I'd point that out if you ever wondered why, in relationship to the movement of water. It's pretty interesting. Now, a lot of us, if you've, I remember as a kid the excitement of driving to the beach. I remember going to Daytona Beach in Florida, and after that long drive from New York, I lived in upper state New York for a long time, and we drive down there, and it was so exciting. You could smell the ocean, and then eventually you could feel, because we didn't have air conditioning in our car when I was growing up, we'd have the windows down, and you could feel the cooler air as we got closer to the ocean. And the smell, it was just exciting, and it was just really amazing. And what you're experiencing, though, is sort of the evaporation and the cooling effect of water cooling the air as it binds and absorbs some of the charges as it goes up, and cooling the air. We feel that, but there's this heat capacity, high heat capacity that water has. So as the water is sitting there, the sun temporarily breaks the bond because of the characteristics of the type of energy that the sun has, which we all feel. Of course, it causes sunburns and the like, but that heat energy temporarily disrupts some of the hydrogen bonding. But the hydrogen bonds are quickly formed again, and it comes back. So it's a ability to absorb this heat from the sun. And as the net result is, you start to feel the coolness of this evaporation as the water goes up, because the sun's hitting the bonds and the like, but it's absorbing this energy from the sun. So while the sun energy may make sand very hot, so you can, I don't know the last time you've been at the beach, but guys, it's really difficult to look tough and in front of the ladies and all that, walking on the sand while your feet are literally boiling and burning, the skin's falling off and everything. Just joking. But as you're walking on the sand, you get under the water, and it's nice and cool, and it feels a lot better. Because the heat capacity with the sand, thermally, it just absorbs and absorbs and absorbs, and it gets hot. Literally, the sand just takes that heat, where the water will dissipate that, and that's what they mean by high heat capacity, because it's breaking down that energy. So that energy was actually utilized to break the bond, but immediately forms it back, and you can see this temperature differential as a result. And that's all it was about that. Lower density when frozen. Water has this characteristic. Hydrogen bonding arranges water molecules to a crystalline-like lattice, and you can see it's equidistant and spaced, and so as a result of that, ice is less dense and it floats. And if you ever wondered why that's the case, this is because of hydrogen bonding. As you decrease the molecular movement, now if I heat the water, this is moving, and it's really kind of hard to see this in a static picture, but because of there's a type of movement called Brownian movement, and these molecules start to shake, and when it's shaking, it's more active, and it's liquid. But when you start to chill it, the activity slows down, so the very weaker forces, it'll cause it to align equidistantly based on the least amount of charge, and it forms this lattice structure, and as a result it's less dense, and it starts to float, and that's why ice floats, and water is of course more dense, and it sinks. And so the relative area occupied by the same number of molecules, you can see frozen water, it takes up more space than liquid. And it's because of this lattice structure. And that's why we see what we see, and the ice cubes float and all that stuff. Lower density when frozen. So low density is a solid, ice floats. It's unusual since most substances become more dense when frozen. As the molecules slow down, they pack together more and more efficiently. But that's not the case for the water, as I've already explained. Each V-shaped water molecule, because of its bipolar nature, via hydrogen bonds forming that crystalline lattice. So you can go back to look at that figure. Um, the feature of the water causes lakes and other body waters to freeze from the top down. As a consequence, they're less likely to freeze completely, which of course that provides life ability to have liquid water even under some ice. So water is a good solvent, and this is why we always look for water in other planets, because it's required for life. But you can take the sodium chloride ion, chloride ion, and it forms a sodium chloride crystal, table salt, and it will be dissolved in water because the water molecule will flip around and neutralize the charge of each of those ions, and that's how it dissolves. So if you ever wondered why things are dissolving, now you understand, because water has that bipolar characteristic, and it will just cover it with that opposite and neutralizing the charge of these ions, and there you go. And so hopefully, if you ever had that question on how that works, now you can impress others by telling them such. So we've talked about a lot in this section. I'm going to stop at this point. Hydrogen bonds between water molecules gives water several of its most important characteristics: cohesiveness, reduced density as a solid, the ability to resist temperature changes, because of course the energy is being used to break bonds instead of heating it, and broad effectiveness as a solvent for ionic and polar substances. So it's really interesting. I hope you enjoyed this section. Next time, part 3, we're going to be talking about some other characteristics of water, like pH and that sort of thing, and I hope you'll enjoy that section, and you have a good time looking through this material, and I hope this answered some of the questions that you may have had just about some things that you observed in nature. So until next time, please be safe.